Math 1343, Week 8, Video 7. A complete example of a goodness of fit test. Full disclosure. The federal data on the board does come from federal data. These aren't made up numbers. I will admit that I did pull them from a Wikipedia article, so they're only as reliable as whoever put them up there, but they are cited as being from the 2019 U.S. Census Bureau. The other disclaimer is the verbiage and grammar and capitalization was taken directly from this U.S. Census Bureau report. I don't want anybody to read anything into the choice of words or the choice of capitalization or lack of capitalization, as it was copied verbatim from the U.S. Census Bureau report. All right, according to that report, 60.1% of the population is non-Hispanic white, 18.5% is Hispanic or Latino, any race, 13.4% is Black or African American, and the remaining 8% identifies as another race. A company employs 90 white employees, 30 Hispanic employees, 20 Black employees, and 10 Asian employees. Does this fit federal race distributions? I also want to put out a disclaimer that I am not trying to make any comment about equal employment opportunity, about hiring practices or anything. This is simply to demonstrate how you would answer the question, does this distribution of employee races at this company match the distribution of employee races, of races for all of the population? Or if it differs, does it differ by a significant amount? All right, we're going to do this using both the critical value approach and the p-value approach, because once we do one, the other one's pretty quick to follow. All right, let's just go through the steps, starting with the hypotheses. Instead of writing the hypotheses in terms of the proportions, we could say PW equals this, PH equals this, PB equals this, and P, I guess A for another or O for other equals this. Or we could just say that the null hypothesis is the company's employees fit federal race distributions, meaning that the proportion of each race at the company is close enough to the proportion at the federal level. And the alternative would pretty much say the company's employees do not fit. The company's employees do not fit federal race distributions. Or whatever, however we would word it. Just try to find a good way of saying it fits or it doesn't. The super generic way is that the sample fits the population claim and the sample doesn't fit the population claim. But I don't want hypotheses as vague as that. All right, step 2 depends upon whether we're going to do the critical value approach or the p-value approach. Let's start with the critical value approach. If we do the critical value approach, our next move is to locate the critical value, the rejection region, and the non-rejection regions. This will be a chi-squared test, chi-squared distribution. And remember, that is non-negative, so it starts at 0. And it's always a right-tail test. Chi-squared is always a right-tail test. Let me rephrase that. Goodness of fit test is always a right-tail test. There do exist applications of the chi-squared distribution that are two-tailed, and dare I say left-tailed. All right, we need degrees of freedom. You know what the degrees of freedom will be. The degrees of freedom is the number of categories minus 1, which is equivalent to the number of proportions minus 1. We were given 1, 2, 3, 4 proportions, 4% if you will. Therefore, there are 4 categories. Therefore, the degrees of freedom is 4 minus 1, which is equal to 3. We were not given a significance level, and that was on purpose Do you remember what significance level we use in the absence of a clearly stated one? The answer, 5%. So we are assuming a significance level of 5%. So we would get a chi-square distribution, which I happen to have right here. And we would go to the third row and go to the 5% column. In the third row, in the 5% column, our chi-squared value is 7.815. If you were in my class, the directions for this would also say to label the regions. So NRR for non-rejection region, RR for rejection region. And now we're done there. This is our critical value. Step 3 is the part that takes the most work, because step 3 is to calculate the test statistic. But in order to calculate the test statistic, whose formula is chi-squared equals the sum of some fractions, the denominator is the expected values and the numerator is the square of the difference of the observed value and the expected value. But in order to do that, we have to calculate our expected values first. So let's make a real quick table of race, observed values, and expected values. And if you notice, I'm making this one using columns, which is actually nice because when we work out the expected values, we can just work them out left to right. For our races are white, Hispanic, Latino, Black or African American, and then other. Our observed values were 90, 30, 20, and 10. I'm going to write the word other here. That looks like a number 0. Our expected values we have to calculate because the expected value is the sample size times each proportion, except we weren't given a sample size. However, we have enough information to calculate it. The sample size is simply the sum of our observed values. So if we were to add up this column, we would get 150. So for each expected value, we have to multiply the sample size. Out of a sample of 150, we would expect 60.1% of them to be white, so we would multiply that by 0.601, or 60.1 as a percent, as a decimal, excuse me. And in fact, on all of these calculations, we would multiply 150 times each of the proportions. 18.5% for Hispanic and Latino, 13.4% for Black or African American, and 8% for other. So this part's pretty easy. It's just a little bit of calculator button pressing. 150 times 0.601 is 90.15. 150 times 0.185 is 27.75. 150 times 0.134 is 20.1. I'm going to write 0.10 just to be consistent with the 2 decimal places. And 150 times 0.8 is exactly 12. Guess I don't need those extra zeros, but we'll make it a significant digit consistency. All right, so now that we have all of the expected values, if you just take a quick glance at what we observed versus what we expected, they're not that far off. We observed 90 white employees, we expected 90.15. Pretty close. We observed 30 Hispanic and Latino employees, we expected 27.75. So that's actually a little bit higher than what we would have expected. Something is amiss here. Let's keep going. 20.10 is what we expected for Black or African American employees, and we saw 20. And we expected 12 other employees, and we saw 10. So 1, 2, 3 of them were above what we expected, and 1 was below. Okay, I thought they were all above, and that would have been bad because they have to balance out. All right, so we need to calculate our test statistic by setting up this fraction for each category, for each race. So, for white, we observed 90, but we expected 90.15. That difference will get squared and divided by 90.15. You know what? I think we can do something to make this a little bit easier. When we set up this formula, it gets really congested, but maybe we can use this chart to help us not make this so congested by just doing the subtraction problems here. And then we can import the results of the subtraction problems up here. All right, so observed minus expected. 90 minus 90.15 is negative 0.15. Don't need a calculator for that. 30 minus 27.75 is 2.25. Don't need a calculator for that. 20 minus 20.10 is negative 0.10. And then 10 minus 12 is negative 2, or negative 2.00. You may notice if we add all these up, they'll be 0. If you think about it, it has to be. But by calculating the differences in our table, it'll make it a little bit easier to set this up. The first difference was negative 0.15. That gets squared and divided by the first expected value, which was 90.15. And I'll be honest, I don't even need this negative. It's getting squared anyway. When I put it in a calculator, I won't type it. The next difference was 2.25. That gets squared and divided by the expected value of 27.75. The third difference was negative 0.10. That will get squared, and again, the negative is kind of necessary there, and divided by this expected value of 20.10 plus negative 2 squared. You know, I feel really silly writing negative 2 squared because first off it's positive and secondly it's 4. But for consistency, it won't always be obvious what the squares are. I'm going to write it down. The difference squared divided by what we expected, which was 12.0. Therefore, our test statistic will be chi-squared is approximately whatever this equals in a calculator. I'm going to call it out. I'm not going to type a single negative on top because they all disappear anyway because they're getting squared. 0.15 squared divided by 90.15 plus 2.25 squared divided by 27.75 plus 0.10 squared divided by 20.10 plus 2 squared, feel silly typing that, divided by 12. Luckily I have a display calculator. I can scroll back to make sure I typed in what I meant to type in. And if you have a display calculator, it's not a bad idea to scroll back, look over what you typed to make sure that there aren't any errors, because it is easy to make a typing error, a keystroke error, when you're pressing so many keys. But I checked it, and I got 0.5165 rounded to 4 decimal places. I'm not going to enter it again, but I am going to go back and look at what I typed in just to make sure that I didn't make a mistake. And believe it or not, it's not a bad idea to invest this time in checking your calculator work, because there's nothing worse, especially if you're using online homework, to have everything set up great, make one small error, and get no credit. If it's a handwritten test, you could get a lot of partial credit for writing out the expression for the test statistic, even if you miscalculate it. All right, so we have our test statistic at 0.5165. So as a critical value problem, it's over. This is a really small critical value, really small test statistic, and relative to the critical value, it is way over here, almost 0. So it's very much in the non-rejection region. So we do not reject the null hypothesis. And let's go ahead and answer the question, which was, does this fit federal race distributions? Well, we didn't reject the null, and the null says it fits. So we'll just say, for the sake of space and time, it fits. So if this were my class and a test question, I would expect you to write and answer the question as a complete sentence in the context of the problem. But what if this were the p-value approach? I'm not going to erase anything, but we'll address the p-value approach down here in a different color. Let's use green. if we did the p-value approach, remember how it differs from the critical value approach. You still write the hypotheses, but you don't do a test statistic or rejection and non-rejection regions. You do calculate the test statistic, but before you make a decision, you find the p-value, which is the area of the tail cut off by the test statistic. Still a right tail test. So we would cut off a tail. We still have degrees of freedom of 3. And our tail's area, we don't know the area. We're going to look that up or get a range of values for it. Our test statistic was 0.5165. Actually, that would be way over here. It's almost 0, so our test statistic is way over here. 0.5165, but it's still a quote-unquote right-tail test, which means we would shade all that and we would need to find this area. That'll be the p-value. So we would go to our table and figure out the 2 areas that our p-value is in between. So I'm going to the third row in the chi-square distribution, and I'm looking for a chi-squared value of 0.5165. Going across, there is a chi-squared of 0.352, which is less than that. And there is a chi-squared of 0.584, which is greater than that. Those 2 chi-squared values that bound this have right tail areas of 95% and 90%. That means our p-value is greater than 90%, but between 95%. What that means in the context of the problem is if the null hypothesis is true, then the probability of a company's employees having this distribution is between 90 and 95%. Okay, well that's pretty likely to happen then. But in terms of the p-value approach, once you calculate the p-value, the area of the tail cut off by the test statistic, then you compare it to the significance level. We weren't given a significance level, so we assumed one that was 5%. I don't know the p-value, but it's clearly bigger than 5%. The p-value is greater than 5%. Therefore, we do not reject the null hypothesis, just like we did before. I personally prefer the critical value approach, but that's just my own preference. The p-value approach, when you get the p-value, it tells you the probability that your sample would have occurred under the assumption that your null hypothesis was correct. All right, so goodness of fit test, it's really not as bad as it seems. It really slows down when you calculate the expected values and then the test statistic, but it's really not that bad. You just have to stay focused, be careful using your calculator, and the rest is pretty easy.